Hello. All right. Hello, everyone. I hope you can hear me well. If not, let me know. Okay. Yeah, please let me know if you can hear me. Just to say something in the chat. Ah, brilliant. Okay, perfect. So we don't have too many people today. That's fine. So what I want to do today is briefly introduce the derivatives, and next week we'll do gravity, and the week after, on the 3rd of November, David Vaccaro is going to do a webinar on derivatives properly. Okay, so today it's half and half. I got 4 problems on derivatives and 3 problems on gravity. And let's get to it. I'll share my screen. Okay. Problem one. Find the partial derivatives of the first and second order. So how to do that? And this is actually quite simple. The partial derivatives of the first and second order. The partial derivative is du, and let's say dx. That's the partial derivative. To find the partial derivative, we treat y as a constant. Okay. So how would that look like if we treat y as a constant? It's going to be x to the power 4 plus c minus 4x squared times, well, let's call it d, right? So this is what we are thinking. This is what we're thinking about. And we just find the derivative of that, and that's 4x cubed plus 0, because the derivative of that is 0, minus 8x d. Okay, well, remember d is in fact y squared, so we just put y squared. Okay. Do you understand what I just did? From 1 to 10, please, in the chat. Okay, brilliant. Okay, so I can go a little bit faster, I guess. So what I've done, I found the derivative of this function. The function is u, is a function of 2 variables, x and y. I just said, so let's say y is constant. I'm going to fix y, and I'm going to find the derivative. Now I want to find the derivative with respect to y. And this means keeping x constant. So the derivative of this is 0 plus 4y cubed. Now 4x squared is a constant times 2y. So it's going to be minus 8x squared y. Because 4x squared is a constant, we differentiate 2y, x squared, y squared, we get 2y. So let's write it down, 4y cubed minus 8x squared y. Now we find these are the first derivatives, first partial derivatives. Let's label them first partial derivatives. Okay. And now let's find the second partial derivatives. Okay. So we find the derivative of this, so it's the derivative dx of that, 4x cubed minus 8xy squared. So this is going to be 12x squared. That's easy. Now what to do with this one? Well, 8y squared is a constant. 8y squared is a constant, so we just the derivative of x. So it's minus 8y squared. Yes, is there a question? Okay. 8y squared. Brilliant. Now we find the second derivative with respect to y, dy squared, and that is the derivative of with respect to y. Apologies for my handwriting. Of this expression, 4y cubed minus 8x squared y. And this is 12y squared minus 8x squared. The partial derivative is the rate of change of a function in one particular direction. So let's have a look. For example, let's take a 3D graph. So this is a very useful tool if you like to draw 3D graphs. And let's add a surface. Well, perhaps not this one. Let's make something simpler, like 0.001x squared. Okay, too far off. Okay, that's reasonable. Plus 0.1 y squared. So this is a surface, and you see this is x. So it's the rate of change in this case. U is the height above the xy plane. Z is u of xy. And if you're at a point, let's say if you're at a point 1, 0, this is 1, 0. This is the rate of change. So du dx is the rate of change of z in the x direction. And du dy, the gravity assignment is here. Here's a link, and here it is. Okay, this is it. Gravity assignment draft. We're very sorry. We are working very hard to get it online, but this is pretty much the assignment. It hasn't been proofread, and there will be very slight changes, but you can access it here. So just like the dy dx is the gradient, dx dy, du dx is the gradient in that direction, and du dy is the gradient in that direction, in the y direction. So du dy, dy is the gradient in that direction, is the gradient, Okay, and this one is the gradient du dx in the x direction. So hope that makes sense. So this is one of the things it is used for. That's the meaning of it. But it has lots of uses. One of them is described in the assignment. So it's finding the approximations. And the third part, second order partial derivative, is the mixed one. It's the d squared u over dx dy, or dy dx, which is the same thing, d squared u dy dx. So it's the it's the d dy of du dx. du dx. So it's d dy of this expression of 4x cubed minus 8xy squared. And if we find this, the derivative of this with respect to y, this is very important that it is with respect to y. And we get, this is 0. This is 0, and this is minus 16xy. This is the mixed second order derivative, this one. This is the second order with respect to y, second order with respect to x, and yeah. Okay, so how well do you understand what we've done here in question in the first problem? On a scale of 1 to 10, as usual. Okay. All right. Brilliant. Okay, very impressive. Okay, problem 2. Sketch the following surfaces and describe the contour lines. Okay, so this is not the easiest question in the world, but let's, to understand what it is, let's say, let's set y is equal to 0. Then z becomes sine x squared. And it would be useful to draw this graph. So what I'll do, I'll just do a quick sketch. No, there's not, because you can't have derivative with respect to x and y. It's either x or y. Well, I mean, it's a very good practice just trying to understand how this looks like. How this looks like. I mean, it starts with 0, and then, well, sine of x. Well, it should be pretty much like sine x. So what's happening is this number increases faster than x. That means that the period will decrease. Okay, this is sine x squared, and this is x. And let's confirm that. Y is equal to sine x squared. And here it is. Actually, the middle bit goes like x squared, so I wasn't entirely correct. It's more like this, more like this, and like this. Okay, so which is useful just to understand what the 2D or 1D version of it looks like, depending on how you look at it. The 2D version. Okay. Now we can notice that if we are on an XY plane, so this is X and this is Y, this is the XY plane. If you have a point with coordinates X and Y, then the distance from 0 is R, and R squared is X squared plus Y squared. So what we can notice is that this expression Z equals sine. So this is going to be a 3D graph. Yes, so this is Z, X and Y. Oh, sorry, X and Y. Yeah, don't draw it like this. X goes here, Y goes here. This is the standard triplet. Sine of X squared plus Y squared. But in fact, what it says, it's sine R squared, where R is the distance from 0. So basically, because this is R in the direction of X, isn't it? It's the same thing. So it behaves exactly the same way in all directions. So the function behaves the same way in all directions. And basically, it's this thing. It's actually the rotation of this shape around the z-axis. Let's have a look. So it's going to be like this in all directions, like this, and it goes down like this, like this, like this. Well, let's draw it. Sine, open bracket, x squared plus y squared. And just to make it prettier, I'm going to change the range. You can see from the side, it looks very similar. I'll just limit this to -1 to 1. And you can see the same shape. Yeah, middle, bam, 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 bam. And that's in the x direction. And then just change this to from -8 to 8. And you get surface. Which I think is pretty cool. Now here you see secondary circles. These are fake. These are not real. This is just an aberration of the just an operation. It should be perfect circles, just like droplets on a surface of the water. Imagine you drop something in the water and you get waves radiating out in all directions. So that's pretty much the picture that you see. Although the wavelength shouldn't change, so not exactly the same, but very similar. And describe the contour lines. Well, this is a kind of a tricky one. The extra circles are due to the limited resolution of this system, of this program. Okay, if you make 640 samples, 640, increase the resolution, and you see it's much better. Okay, yes, I increased the resolution, and now we don't see any aberrations. Okay, I'm fairly new to this software, so it's a better way of looking at it. So what you need to understand, this is a 3D graph, and 3D graphs are drawn like this. So the Z and X and Y, where you had a 2D graph, you had Y of X is equal to, I don't know, sine X. This is a 2D graph. And here you have U or Z, which depends on X and Y. And in this particular case, it's sine of X squared plus Y squared. A very popular one is just without the sign, X squared plus X squared. And it looks like this. You had this one in, so reduce the sample size. You had this in the assignment. There is this is one of the examples. So yeah, here it is. This is the surface. This is a paraboloid. And another very popular one is X squared minus, so just take it from minus 2 to 2, and here from minus 2 to 2. We also call it a saddle shape because it's in the shape of a saddle. It's quite beautiful. And if you look at it from this point of view, you see that it's a dot. That means you can fit a straight line. You can fit a straight line along this surface, just like this, across, and it's going to be a straight line. Why are the extra circles? So why does it have the same way? Why does it behave the same way in all directions? Because X squared plus Y squared is R squared. And R squared is the distance from 0. So it depends. So it's the sine of the distance from 0. And it doesn't matter which way to calculate the distance. Like points on the same circle would have the same R. So for each of these points, X squared plus Y squared is the same value. Therefore, these points, to this function, these points are identical. All the points which are equidistant are identical. Okay, the contour lines, I don't think I really want to do the contour lines. Do have a look at the contour lines for the paraboloid. So the contour lines is basically view from the top. And So do look in the assignment. So this is X and this is Y. Contour lines for X squared plus Y squared equals Z in this particular case. And for different Z's, so it's going to be X squared plus Y squared equals constant, because for a different Z. And the contour lines simply are circles. So these are the lines of equal height or equal potential. Sometimes we call them equipotential lines. So this is Z equals, I don't know, 7, Z equals 3, Z equals 1. It's a view from the top, and these lines are on the same height. Okay. So just for you to understand what I'm talking about, these contour lines can be drawn here. So the bottom contour line, the bigger contour line, and the bigger contour line. So Z equals 1, Z equals 1, Z equals 3, and Z equals 7. So this is, when they say contour lines, this is what we mean. So this is that contour line, and this is that contour line. So basically a contour line, just like on a map, is a map of equal height above. Yeah, we count the height from the XY plane. This is XY plane, and this is the height above that plane. Well, it's Z. Z is the height above that plane. Hope that makes sense. All right, let's move on. Let's move on to the interesting ones. Find the first Taylor approximation of this. Find the first Taylor approximation of this function. Oh, sorry. And of course, this has to be y. So this is a 2D Taylor approximation. Have you done Taylor series? 1 or 0 in the chat, please. 1 for yes, 0 for no. Taylor series, about half and half. Okay. Maybe I should talk about Taylor's first. Oh, yeah, Maclaurin's. Have you done Maclaurin's? Sorry. When I say Taylor, I mean Maclaurin. Okay, some no, some yes. Maclaurin and Taylor series are pretty much the same thing. It's just the Maclaurin series is we find the approximation at 0. To understanding Taylor series and understanding how important it is. Understanding. Let's go somewhere. Oh, we don't have. Okay, here. Understanding Taylor series. Maclaurin. I'm pretty sure I prefer Taylor because I don't know how to spell Maclaurin. But I think I have the Maclaurin spelled correctly here. Now, imagine your calculator, right? You have a calculator, you all have one, and you put sine 42. Like, how does it know? How does your calculator know what sine 42 is? Well, perhaps it has a table, yeah, and it knows the sine of every single angle. But then you give it sine 42.5. Does it have a table for that? Does it approximate looking at sine 42 and like that's 42 for line 43? Well, the answer is no. The calculator uses an approximation of sine called the Taylor approximation. And to the best of our knowledge, well, to a very good degree of accuracy, sine x can be approximated by x minus x cubed over 3 factorial plus x to the power 5 divided by 5 factorial minus x to the power 7 times 7 factorial. I hope you see the pattern, plus etc. plus, so it's going to be x to the power 2n plus 1 divided by 2n plus 1 factorial. No, in this case, x is in radians. In this case, x is in radians. The calculator converts degrees into radians, calculates the value of the sine, and then goes back to degrees if it needs. Like, how is that? How does that work? This is a polynomial. This is a polynomial approximation. And you know the first part of it. You know that for small angles, sine x is approximately x. So you've already seen that before. The more terms you have, the more accurate is the approximation. The more terms you have, the more accurate the approximation is. Okay, let's have a look. Let's draw y equals sine x. And now we have y equals x. Look, for small values of x, indeed, they are very close. They are very close here. But you can make that better. You can put x minus x cubed over 3 factorial. And you can see it gets even better. It gets curvy and closer to the actual thing. And then you add x to the power 5 divided by 5 factorial, and it gets even closer. And then you do minus x to the power 7 divided by 7 to the 7 factorial. Now, by this time, the middle bit is probably a good approximation to the, look, they are the green and blue lines, they're pretty much the same thing. Okay, zooming in, I can't see a difference between them. Okay, it'll take me a while to zoom out. For small values of x, this is a very good approximation. The bigger the value of x, the more the discrepancy between the two. Like here, it's quite far apart. But that's what a calculator does. It approximates. And the computer as well. The computer is not very different from a calculator, just more powerful. But the computer doesn't know what sine is. Oh yes, the general term is -1, sorry. I got yes, -1 to the power n, of course. Good. Is it 2n minus 1 factorial? Well, yes, 2n plus 1 factorial. And this is what we do. The two-dimensional version of the Taylor approximation also works. It's just a little bit more complicated. And if you have a Taylor, if you have a two-dimensional function, u of xy, the Taylor approximation delta u is the approximation of the change in u, is approximately equal du dx delta x plus du dy delta y. Right. So this is a tricky one. It's a tricky one because you just need to understand what is what. What is u in this particular case, and what is delta u? We need to understand. Well, as a matter of fact, in this particular case, u is x to the power m and y to the power n. Delta x is x, and delta u, delta y is y. Now this is probably the hardest bit because of this super confusing notation. Now, so what we actually mean is this. This is what we actually mean. And this is x. And this is x. And the function, so u of x, y is equal to x to the power m, y to the power n. I've already mentioned that before. And u of x plus delta x and y plus delta y is equal to x plus delta x m, x plus delta y, y plus, that's y plus delta y n. Right. So I hope that makes sense. Now, so now we can find du dx. So we keep y constant. So it's going to be m x to the power m minus 1, y to the power n. And similarly, du dy, it's going to be n x to the power m, y to the power n. Minus 1. Now we find u of 1, 1. U of 1, 1. Well, it's 1 to the power m, y 1 to the power n, which is 1. And delta u, according to this formula, is du dx delta x plus du dy delta y. So du dx is m, but of course we're talking about the point 1, 1. So m times 1 times 1, so it's m, plus n times 1 times 1. So m delta x, sorry, plus n delta y. Okay. So that's that. So we have u, so u is equal u at point 1 plus delta x, 1 plus delta y is equal to u of 1, 1 plus delta u, which is m delta x plus n delta y. Swap the terms in the equation. Where did I do? Oh, these terms. Because they switched the terms in the equation. The equation was 1 plus x m and 1 plus y to the power n, and x and y are small. Right. Now we have this, and we can rewrite this in terms of x and y. So u of 1 plus x. So we replace, we do a backwards substitution. 1 plus y is y of 1 when 1 is 1. So it's 1 plus mx plus ny. The link to the whiteboard. Here you go. And finally, but that's it. That is y. That is this thing is 1 plus x to the power m, 1 plus y to the power n. So this is the approximation. 1 plus mx plus ny. Let's see if this is let's see if it actually works. Let's say we want to find 1.002 to the power 7 multiplied by 1.03 to the power 2. So it's the same as 1 plus 0.002 to the power 7 times 1 plus 0.003 to the power 2. So it's going to be 1 plus 7 times 0.002 plus 2 times 0.03. Like this one and this one. Well, remember, we said that u of xy is x to the power m, y to the power n. So if we replace x with 1 plus x, and y we replace with 1 plus y, we get 1 plus x to the power m and 1 plus y to the power. Okay, right. Yes, I will recap. Sorry, this is quite complicated stuff. Let's see if this is a good approximation. So we just grab a calculator and we do 1 plus 7 times 0.002 plus 2 times 0.03, which is 1.074. And this thing, just grab the same calculator, 1.002 to the power 7 times 1.03 to the power 2, which is 1.0758. So it's pretty close. So this is pretty close to that. Not the same, but it is an approximation. So what we did is we found that this is an approximation of this. Now, why would we use this approximation? Somebody tell me, why would we want to use this approximation? Why don't use this thing? Why would we need such an approximation? For faster computing, absolutely. Yeah, I mean, 1 plus mx plus ny is way easier than 1 plus x to the power m. What if m is 1,000? What is the power power of 1,000? A computer will tell you, no way I'm doing that. Okay, or the computer would probably use an approximation itself. But because if not, multiplying by itself 1,000 times is very, very costly. Okay, so what I have done, I have been asked to find an approximation of this. And I said, let's say we have this function. So this is a function of two variables, x and y. And then I replace x with x plus delta x and y plus delta x, and I have this. And given that delta x and delta y are small, I can use the Taylor approximation, which is given in the assignment. There is a proof of that. And then we substitute x is equal to 1, y is equal to 1. We substitute into here. Delta x is x and delta y is y. I know it's super confusing that we replace delta x with x, but yeah, bear with me. And if we do this substitution, we actually end up with 1 plus x m 1 plus y n. Okay, and then we find u of 1, 1. We use the formula for delta u. Delta u is this, and then that. I will do another example, so hopefully that makes more sense. So and it's an easier example, by the way. Find the approximate value of 1.002 times 2.003 squared plus 3 times 004 cubed. Well, we need a function. We need a suitable function. And the suitable function is u equal x times y squared times z cubed. And we substitute, so x is equal to 1, y is equal to 2, and z is equal to 3. Because 1.002 is approximately 1, 2.003 is approximately 2, and 3.004 is approximately 3. So that is, so u, we find u of 1, 2, and 3 is equal to 1 times 2 squared times 3 cubed, which is something. 1 times 4, 4 times 27, it's 108. 108. Now u of 1 plus delta x, 1 plus delta y. So delta x, of course, is 0.002. Delta y is 0.003. And delta z is 0.004. And 2 plus delta y, and 3 plus delta z can be written as well, this. So it's going to be 1 plus delta x, 2 plus delta y squared times 3 plus delta z to the power 3. Okay, bear with me. We use the formula. We use the formula that delta u is equal to du dx delta x plus du dy delta y plus du dz delta z. Now you can see that we went from two variables to 3 variables. Thus is if this was a graph, this would be a 4-dimensional graph. We don't know how to draw those, but a 4D function exists. Why not? So we need to find du dx. So this is the function that we've started with. So du dx, that is in fact du dx is y squared z cubed. Du dy is 2xy z cubed, and du dz is 3xy squared z squared. So delta u is equal to y squared z cubed delta x plus 2xyz cubed delta y plus 3xy squared z squared delta z. And delta u at point 1, 2, and 3, when x is 1, y is 2, z is 3, we just substitute. So that's 4 times 3 cubed, so 108 delta x, plus 2 times 1 times 2, that's 4. 4 times 108 delta y. 3 times 1 times 4 times 9. 3 times 36. 108. 108 delta z. Okay. So in other words, U, in other words, U, yes, U of 1 plus delta X, 1 plus delta Y, 1 plus delta Z. Oh, sorry, 2 plus delta Y, 3 plus delta Z can be approximated by U of 1, 2, and 3 plus delta U plus delta U. Or in other words, 1 plus delta X, 2 plus delta Y squared, 3 plus delta Z cubed is approximately equal to 1, 2, and 3. So that's, what's that? That's 108. Again, the magical number 108 plus delta U. It's 100. Is this bit? So it's 108 delta X plus delta Y plus delta Z. Delta Z. So in other words, 1 plus 0.001. So 1 plus 0.01. Is that what it is? No, 0, 2, 3, and 4. Sorry, 0. How many zeros? 0.00. 0.002. 2 plus 0.003. And 3 plus 0.004 to the power 3 to the power 2 is approximately equal to 108 plus 108 times 0.002 plus 0.003 plus 0.004, which I assume I can calculate without a calculator. That's 7, 9, 0.009. Okay, no, I don't think so. 108 times 0.009 is 0.972. So it's 108.972. So that's the approximate value. And what do we get if we actually calculate the original value? 1.0, so 1.002 times 2.003 squared times 3.004 cubed. 108.975. So the calculator says that this is 108.976. So reasonably close. Okay, and this is only the first order approximation. We're not taking the the second order. Yeah, this is equivalent to taking the first approximation. So sine x is approximately x. That's what we say the first approximation. The first approximation of sine is x. The formula comes from, why is that delta u? Delta u is the change in u. Is the change in u. So hope that makes sense. Okay. Now this problem has a backstory to it. So basically, there's a conspiracy theory that that gravity is not what we think. Basically, somebody is trying to hide gravity from us. I'm not particularly I don't particularly understand the logic behind it, but basically there are people who claim that gravity is not real, etc., etc., etc. In one of their arguments, yes, if x and y and z were bigger, that approximation would not work that well. Absolutely, that is true. And one of the problems, I won't do the problem, but I will describe what it says. So basically, you have the sun, and you know that the Earth goes around the sun. So the Earth goes around the sun, and the moon goes around the Earth. And at some point, when the moon is between the Earth and the sun, well, we know gravity. It experiences gravity, and this the force of gravity. The one way, because the sun is attracting gravity from the sun, and the force from the Earth. And which one do you expect to be bigger? The force from the sun or the force from the Earth? If you were the moon, which one are you more attracted to, the sun or the Earth? Absolutely. I mean, yes, it is closer, and you are, after all, going around the Earth and not around the sun. And you know the formula. The formula for the sun, you take the gravitational constant, the mass of the sun, the mass of the moon, divided by the distance, which you can look up in wonderful Google, R1, and the force of the Earth is G M Earth, M moon, divided by R2. And the thing is that when you actually do the calculations, you will find that F sun is bigger than F Earth. Infinite question marks. Oh, yeah, of R squared, of course. Sorry. They use this. This is their argument to prove that Newton's law of gravity is fake. Gravity is fake. The Earth is flat, etc., etc. Okay. So this is what I want you to look into. Okay, I want you to bust this myth. The calculation is correct, and there's no trick there. The force is bigger. This is something you'll need to explain. So good luck with that. That's all what I'll say. But what do you mean? It's at the moment when it's going between the moon and between the Earth and the sun, it's perpendicular. It's moving straight ahead. It's moving perpendicular to the line connecting the Earth and the sun. It has no momentum either way whatsoever. It can go left. If you can start orbiting the sun, or you can start orbiting the Earth. So the moon is traveling at a right angle with speed v, and it can turn left or it can turn right. And apparently this force from the sun is bigger, so it should be turning left. But it's not. Or is it? So this is what I want you to look into. Okay, don't spoil stuff for others. If you guessed it, if you understand the reasoning, don't spoil it for others. It's fun. It's fun to it's the pleasure of finding things out. Okay, that's one of my favorite books, The Pleasure of Finding Things Out by Richard Feynman. What do we have? Do we have time for? Yes. Okay. Problem 6. A very similar problem is in the assignment. A 1 kilogram satellite is stationary between the Earth and the Moon, such it is attracted equally to both. So we have the Earth, we have the Moon, and there's a satellite, which is 1 kilogram. Well, I mean, it's attracted equally to both. So I'm assuming it's closer to the Moon. Okay, so when the astronauts went onto the Apollo missions, this is the point where the Earth's gravity stops affecting them, stops slowing them down, and the Moon's gravity starts accelerating them towards the Moon. All right, so they need to reach that point, and once they reach that point, they will start falling onto the Moon. Yeah, so if you were in the Apollo rocket, it goes past this point, and then it starts so it's slowing down presumably from here, and then it starts speeding up, and then it orbits the Moon a couple of times, then accelerates, and it needs to go past this point. Once it goes past it, it starts falling onto the Earth, and then it needs to slow down and land on the Earth. Okay, so hope that makes sense. So at this point, so let's delete the extra stuff. So at this point, the force is the same. There are some useful numbers. So approximate values, mass of the Earth, which you can always look up. Mass of the Earth is 6 times 10 to the 24 kilograms. Mass of the Moon is 7.3 times 10 to the 22 kilograms. And the distance between the Earth and the Moon is 350,000 kilometers. The diameter of the Earth is just over 10,000. So the distance between the Earth and the Moon is like 30 times bigger than the diameter of the Earth. It's something not all people don't always appreciate. So this diagram is way off. The diagram is way off. So it would, in real size, it would be like this. Something like this. But so we have the force, which is G, mass of Earth, mass of the satellite, divided by distance. So let's say this distance is x, and this distance is d minus x, because the whole distance is d, divided by x squared. And this is G, mass of the Moon, mass of the satellite, divided by d minus x squared. And because there it is attracted equally to both, we can say that G, mass of Earth, mass of the satellite, x squared equals G, mass of the Moon, mass of the satellite, divided by d minus x squared. G, m cancel. G and m cancel. And you got and you multiply the mass of Earth, d minus x squared, equals mass of the moon, x squared. Now it's easier to substitute here. So mass of Earth is 600 times 10 to the 22, 350,000 minus x squared equals 7.3 times 10 to the 22, x squared, 10 to the 22 cancels, and you get a quadratic equation. Sorry, this square goes here. This is a quadratic equation, which you can solve. So 600, multiply this out. Well, anyways, I'm not going to do this. I'm just going to use my calculator to solve. I don't want to spend time solving a quadratic equation. I mean, it's not the easiest quadratic equations in the world, but I'm sure you know how to solve quadratic equations. The solution to this quadratic equation is x is approximately 315,000 kilometers, which is quite interesting. So it's almost, it's 350,000 is the whole distance. So 315,000. So that's what, 90% of the way ish. What is the gravitational field at this point? Well, the gravitational field would be 0. The gravitational field at this point would be 0. G is 0 because G is a vector quantity. Gravitational field is a vector quantity. I want you to appreciate that. Gravitational, a vector quantity. So both Earth and Moon pull equally. So the gravitational field is 0. Gravitational field strength is 0. However, the gravitational potential is not. Gravitational potential is a scalar quantity. So we have G or gravitational field of Earth plus gravitational field of the Moon, and you add them and you make 0. But the potential from the Earth plus the potential of the Moon is not 0. As a matter of fact, the potential of the Earth is minus G mass of the Earth divided by, in this case, x, minus G mass of the Moon divided by d minus x squared. No, not squared, just like this. And that's the potential. That's the total potential. And GPE is the potential total multiplied by the mass of the satellite, which is 1. So you get a number. This is a number which is less than 0, of course. Gravitational potential 0 at an infinite distance from any objects. Yes, gravitational potential is 0. And gravitational potential near at all other points is negative. Well, yes, because assume that you are at this point. Assume you're at this point. You can't just, you won't be able to drift to infinity from that point. You need energy to get to infinity. What does that mean? At infinity, your gravitational potential energy is 0. So you get this number. I mean, I really don't want to calculate this, but it's going to be a negative number. Or maybe I do. Can I do it really quickly? I guess so. 6.67 times 10 to the minus constant minus 11 times mass of the Earth. So 6 times 10 to the 24 divided by 315,000 million meters plus fraction 7.3 times 10 to the 22 divided by d minus x. So that's 300. So it's 35,000 million. So it's 1.4 megajoules. It's minus 1.4 megajoules. Megajoules per kilogram. And because we multiply this by 1, it's minus 1.4 megajoules. So the gravitational potential energy of a satellite at the neutral point between the moon and the Earth is minus 1.4 megajoules. So what does that mean? That means if you give it 1.4 megajoules of energy, yes, if you give it 1.4 megajoules of energy, it will have enough energy to reach infinity and stop. Well, what does that mean, reach infinity and stop? Well, it doesn't mean anything. But that means it has enough energy to leave the Earth Moon system pretty much and drift into infinity at an ever decreasing speed. All right, so gravitational potential energy, this means that if you give it 1.4 megajoule of kinetic energy, it can drift to infinity and have a total energy of 0. Right, and finally, Kepler's laws. Kepler's laws. So Kepler was, well, probably one of the most famous astronomers of his time, or of ever. Kepler's. So so several astronomers did observations. They looked at the position of planets, and they were making notes. They were collecting data, and Kepler analyzed this data. And he found 3 laws, which were purely empirical, just by looking at the planets, just by looking at the dots. He figured out that each planet goes in an elliptical orbit. So first he assumed that they're going in circles, but then he realized, well, it's like Mercury was a few arc seconds off, and he realized, well, it must be not a circle but an ellipse. That's the first thing he discovered. Each planet goes around the sun in an elliptical orbit, with the sun at one of the foci. So an ellipse is a shape which has 2 foci, And the property is that for any point x on the ellipse, f1 and f2, these are foci, f1x plus f2x is a constant. That's the definition of an ellipse. Secondly, the radius vector swipes equal area in equal time intervals. Equal areas in equal time intervals. What does that mean? And this is purely by observation. He saw that if this is the sun, the radius vector so if the planet goes from here to here, in, let's say, 3 days, and it goes from here to here in 3 days, then these areas are equal. Like when I studied this, I was like, whoa! They had telescopes which were slightly more powerful than binoculars that you can buy for in a pound shop. Okay, maybe a little bit more sophisticated, but all they did, it was just kept looking and measuring, and they figured out this incredibly sophisticated law. Well, not they, him, Kepler, which was, I think it's, which is really cool. And the third law is that the square of the orbital time, is proportional to the cube of the length of the major axis. Well, in other words, for circular orbits, it's proportional to r cubed. But if you have two orbits, basically, if you have the sun and you have two orbits, one and two orbits around the sun, and this is T1 and this is T2, and this is A1 and this is A2. This is A1 and this is A2. This is the major axis. That means T1 squared to T2 squared is equal to A1 cubed divided by A2 cubed. This is the third Kepler's law. But for circular orbits, it says it's just the radii. It's just the radius. Now, Kepler knew nothing about Newton's law of gravity. Newton's law of gravity was discovered after Kepler's laws. So I would like you to imagine that you are Newton, and from these three statements, you need to derive Newton's law of gravity, or insert your name, law of gravity. And it's actually very simple to do. His reasoning was incredibly simple. He saw that, okay, these things are true. All right, so what do we know? We know that that the planets are moving in circles. So they're really close to circles. So it's not a massive assumption And we know that if a planet is moving in circles, with acceleration is from the previous assignment is minus omega squared r. Okay, well, it's the minus means simply is just towards the sun. Let's drop the minus. It's not really important. Acceleration is omega squared r. The minus just indicates towards. And we know that omega is 2 pi divided by t. So it's 4 pi squared divided by t squared r, where r is the distance. R is the radius of the circle. That's the centripetal acceleration. Okay, now the r cubed divided by t squared is a constant. And we will call this constant K, Kepler's constant. So we can rearrange. We can make R equal to Kepler's constant times t squared divided by r squared. R squared. Just some trickiness with numbers, and we sub that into here. So the acceleration, the centripetal acceleration, is 4 pi squared divided by t squared multiplied by r, which is k, Kepler's constant, t squared divided by r squared. T squared cancels, and we are left with 4 pi k divided by r squared. And that's the acceleration of a planet. Well, we know Newton's second law, F equals ma, which is equal to 4 pi k divided by r squared multiplied by the mass, pi squared. Yes, thank you. Right. And let's look at this expression. We can see that the force is 4 pi squared k m divided by r squared. So the force on a planet is a constant times the mass of the planet divided by the radius of the orbit squared. So this is a constant which is the same for each planet. So it depends on the sun. So this constant is actually, as Newton later discovered, is Gm. It's dependent on the sun because it's the same constant for every single planet of the solar system. And we have G m over r squared. And this is how Newton came up with this law, which at that time was like a breakthrough. The universal law of gravity, which we know that works very well for our solar system. It doesn't really work for our galaxy. So it doesn't work for really big and really small, but that's fine. So yeah. Well, I mean, it kind of works for the galaxy, but we don't know the mass of our galaxy, so that there's a problem there. Anyways, that's how physics was evolved. Like, I mean, I really recommend Feynman's lectures. It's called Feynman's lectures. I'm actually listening to an audiobook. The character of physical law. The character of physical law. It's called. And if you have an Audible subscription, it's free on Audible. The character of physical law, and I'm sure you can find it on YouTube. So just listen to it if you have a chance. Just the first 2 chapters, and it's a really nice introduction into this topic. Okay, so I hope that was useful. This introduction to differentiation part 2 and gravity. We'll do next week. We'll do a whole session on gravity, and the paper will definitely be published by then. And also, also David Vaccaro will do a webinar on the 3rd of November. All right. So see you, everyone. Welcome.
Can I ask a quick question, please?
Yeah, go for it.
You know how you said that the gravitational potential, I've read that the gravitational potential is the work done from moving an object from infinity to a certain point.
Yes.
And you also said it was negative. I don't understand. How can work done be negative? Surely it's always positive, but you've said it's always negative. So how does that work?
Work done is not always positive. No, that's not true. Work done is, if you remember, is force times is the scalar product of force times displacement. Or in other words, is force times distance times the angle between the force and the displacement vector. Okay?
Yeah, but then that would require the force surely to be negative. Like if you're moving a block on the table, you'd be pushing it and you're transferring energy, and that's work done, isn't it?
Yeah, but you have a mass above the Earth, yes? You want to lower it down. Which way do you push? Which way are you pushing the mass?
In a negative direction upward.
I'm pushing it up. Otherwise, it would fall down. So I push it up, and the mass is moving down. So the angle is 180 degrees, and cosine of 180 is -1. So it's the force times the distance times the cosine of 180. So it's negative value. Make sense?
Yeah, it just seems a bit strange to me to have a negative work done value for some reason.
Negative work done is absolutely, it's a very usual thing to do. For example, when a car brakes, when you press on the brake in the car, that's negative work. You're slowing down the car.
Oh, because you're applying a force in the opposite direction.
Yes, you're applying the force in the opposite direction of the motion. It's a negative work. Okay.
Okay. All right.
Right.
Thank you.
All right. Right, Jasmine. Yes, we received your work. It will be marked. We will send you an email. Okay. Don't worry. Don't worry. We are on your case. No worries. Okay. Thank you. All right. See you, everyone.